The next problem we're working on is problem number 31. Problem number 31, how tall must a water-filled manometer be to measure blood pressure as high as 300 millimeters of mercury? Now this is actually quite easy. We have 300 millimeters of mercury. Now basically asking if how tall would this manometer have to be if it were made of water instead of mercury. Well, we know that mercury is 13.6 times as dense as water. And so essentially all you have to do is take 300 times 13.6, and that's the answer. So if you multiply that, this is the density of mercury divided and the density of water, then you end up with an answer of 4,100 millimeters or 4.1 meters tall. So it would have to be 4.1 meters tall in order to measure. And that's why, the reason why manometers are made of mercury is to have a small volume to deal with so that they're not so big. The next question is problem number 32, which states pressure cookers have been around for more than 300 years, although their use is strongly declined in recent years. Early models had a nasty habit of exploding. How much force must the latches holding the lid onto the pressure cooker be able to withstand if the circular lid is 25 centimeters in diameter and the pressure in the reads 300 atmospheres? Now the answer book has this wrong because they did the problem as if it said 3 atmospheres instead of 300 atmospheres, and maybe that's what they meant. This is centimeters, by the way. Now the first thing I did was change centimeters change centimeters to meters and diameter to radius, and you end up with a radius of 0.125 meters, so that the area is equal to pi times 0.125 squared. And if you do the mathematics on that, you get an area of 4.9 times 10 to the minus 2 meters squared is the area of that lid. Then I went to the table 2, and found that 300 atmospheres, that 1 atmosphere is equal to 1.013 times 10 to the 5th newtons per meter squared. And you can see why I picked that, because meter squared is what I wanted. If you do the math here, you get 3.039 times 10 to the 7th newtons per meter squared. And then all you have to do is multiply this number times this number. And if you multiply those two numbers together, you get a pressure of 1.4, or a force of 1.49 times 10 to the 6th newtons. Now my mom actually had a pressure cooker, and she got rid of it because she was always afraid it was going to blow up. Now what they actually do with pressure cookers is they'll have a small pop-off valve or a small escape valve, which is usually made of plant or rubber, and when the pressure gets to a certain point, let's say half of this number, that will pop out first and relieve the pressure in the cooker so that it can't blow up and kill everybody in the room or whatever. Now the next one is the first problem, number 37, where we're moving on to Archimedes' principle. In Archimedes' principle, one of the things I always remember is an object that floats displaces its weight, an object that sinks displaces its volume. And that's an important part, is the fact that it displaces its volume. Here it says logs sometimes float vertically in a lake because one end has become waterlogged and is denser than the other end. What is the average density of a uniform diameter log that floats with 20% of its length above the water. Well, the fraction submerged is going to equal the density of the log divided by the density of the water. And so that means that if you want to know the density of the log, you're going to have to take the density of water times the fraction submerged. And the fraction submerged is just that percentage. 20% is above the water, so 80% is below the water. And you turn that into a fraction, so you end up with 1.0 times, and 80% as a fraction is 0.8. So the density, the uniform density of the log is going to be 0.80 grams per centimeter cubed. Pretty simple. The next problem is problem number 40. And problem number 40 is also an Archimedes principle. And it states that bird bones have air pockets in them, which you guys learned in biology if you were paying attention. And those pockets reduce their weight without changing their volume. This gives them a significant less dense bone than compared to other animals, and this is one of the reasons why they can fly, or one of the factors that contributes to their ability to fly. Suppose an ornithologist weighs a bird bone in the air, and its mass in the air is equal to 45.0 grams. Then the mass is also measured submerged, and the mass in water is 3.60 grams. So the first question is, what is the mass the water displaced? Well, this is quite simple. This is going to be 45 minus 3.6, or 41.4 grams. The second question is, what is the volume of the bone? The volume of the bone is equal to the volume of the water displaced, and that's going to be the mass of the water displaced divided by the density of water. And so the volume is going to be 41.4 cubic centimeters. And then using these two pieces of information, you can calculate the density of the bone. It's going to be the mass divided by the volume, or 45, which was its mass in air, divided by 41.4, which is going to equal to 1.09 grams per cubic centimeter, rounded to 3 significant digits. Now this kind of problem will be on your quiz or test. We do several of these kind of problems, and we actually, when I was in high school, this is one of the laboratories that we did, was to do this. Number 42 is a similar problem, a little bit of a curveball, in that we're measuring, instead of the solid object that sinks, we're measuring the fluid that it sinks in. And it says Archimedes' principle can be used to calculate the density of a fluid as well as that of a solid. Suppose a chunk of iron with a mass of 390 grams, so you have iron with a mass of 390 grams in air, is submerged and found to have the apparent mass of 350.5 grams in the fluid. So now the question, the first question, is the following. What is the mass of the fluid displaced by the iron? And again, this is very straightforward. You take 390 minus 350.5, and that's going to equal 39.5 grams. The second question is, that mass of fluid was displaced by what volume of iron? So what is the volume of the iron? Well, the volume of the iron is its mass in air divided by its density, which is 7.8, I believe. Yes, 7.8. And so you get a volume of 50 cubic centimeters. So what is the volume of the fluid? The volume of the fluid, or the density of fluid, is equal to 39.85 divided by 50, or 0.79 grams per cubic centimeter. And if you look that up in the table 11.1, you'll find that this is ethyl alcohol. And densities can be used to find or to identify unknown solids and liquids. One of the things you'll see on television from time to time is they'll be able to show that gemstones that people are claiming are diamonds are not diamonds by dumping them in water. The reason for that is diamonds, real diamonds, are more dense than water and they sink. And cubic zirconium, which is the most common material that's used for fake diamonds, is less dense than water and they'll float on the surface. The last problem is problem number 51. It says a twin-size air mattress is used for camping and has a dimension of 100 centimeters by 200 centimeters by 15 centimeters, which is 1 meter by 2 meters by 0.15 meters. And if you multiply that together, you get the volume of this mattress, which is 0.3 cubic centimeters. It's going to be 2 times 0.15, or 0 cubic meters, excuse me. So that's the volume of the mattress. You're going to need that, so I just went ahead and did it. It says that this has a mass of 2 kilograms. So the question is, what is the weight? How heavy a person could the air mattress hold if it were placed in fresh water? Well, to answer that question, what you have to do is see what is the maximum amount of water that this air mattress could displace. And if you take the density of water, fresh water, times the volume of the mattress, which would be the volume of the water displaced, that's going to tell you the mass of water that's displaced by this volume. In this case, it's going to be our 0.3 cubic meters, and water has a density of 1,000 kilograms per cubic meter. And so that's going to mean that it's 300 kilograms of water can be displaced. Then if you subtract 2 kilograms for the mass of the mattress, that means that 298 kilogram person can get on that. If you multiply that by 9.8, you have a 2,900 approximately Newton weight that can get on that mattress. Now, for some reason, the answer book for the density used 1.21 kilograms per meter cubed. That's the density of air, not the density of water. I have no idea why they did that. So if you happen to have the answer book, you're wondering why the answer is so remarkably different. That's why it's different. Now, quickly, I'm going to go through the questions. I'm not going to go through the definitions, which you can look up and see. This quiz will have some non-problem material on it because we did have some questions. And these questions are on page 393 of your book. The first of these questions is, surface tension is due to cohesion or adhesion or both. Well, as you know, cohesion is the attraction of the same molecules to each other. So, for example, the attraction of water molecules to each other, or the attraction of silver molecules to each other. Whereas adhesion is the attraction of one type of molecule to another type of molecule. So as I'm drawing it here, it would be the attraction of a water molecule to the beaker or the sides of the liquid. Now, surface tension is essentially the fact that water molecules or a liquid's molecules are attracted to each other and do not allow forces to go into the surface of the liquid. And so the answer to number 33 is it's due to cohesion. Now, number 34 is a similar question, but it's asking you about capillary effect, which is fluid going up into a small diameter tube. And in this case, both adhesion, that is the molecule's tendency to stick to the size of the capillary, and cohesion are in play here. So both is the answer to number 34. Number 36 says, water beads up on an oily skin bather, but not on the person next to him whose skin is not oiled. What happens here? Well, basically what happens is you have a balance between cohesion and adhesion. The cohesion of the water molecules to each other and the adhesion of water molecules to either oil or skin. And as it turns out, this is less than this. And so the water molecules will not stick to the oil as significantly as they do to skin. And so the cohesion is greater, the balance toward cohesion is greater, and the water will then bead up. But here, the adhesion and cohesion are more balanced with each other, and so the water spreads out on the skin without beading up. Number 37 said, could capillary action be used to move fluids in a weightless environment such as an orbiting space probe? I think the simplest answer is yes. The fact that the probe is in a weightless environment has no impact on cohesion and adhesion. And so if you had a tube and you wanted to move fluid, the fluid would go up into this tube, and if there was no force of weight against it, it would tend to continue to go up into the fluid and draw by cohesion other fluid molecules into the tube. So my assessment, and I don't know all the factors that would be involved, is that not only would it go up into the tube, but the gravity that stops it at a point like this is not there, so it would just continue to go up until it came out the top. The last question is number 38. And number 38 says, what effect does capillary action have on the reading of a manometer of uniform diameter? Well, the first thing you need to know is when you read a manometer, you read the meniscus. Now, in most situations, the meniscus looks like this, okay? Meaning it's convexed downward, concave downward, excuse me. And you always read the bottom or the midpoint of that. And the reason for that is you have the least effect of the adhesive forces on the sides of the manometer. Now, a mercury manometer, because of the surface tension, or excuse me, of the density of mercury, actually looks like this, where the cohesive forces are much greater than the adhesive force, and you read the top of that, again, the midpoint, which is the top of that meniscus. Now, both these cohesive and adhesive forces are very small, so they don't impact the pressure reading very much, but be that as it may, you have to read the bottom of this type of meniscus or the top of this type of meniscus to get the most accurate reading.